Okay, can everyone hear me? Can everyone see my screen? Excellent. So the agenda for today, because this is the day right before our mid-semester break, is to get through procedures. I like to get past 3.7 right up to 3.8. I think that's a decent amount of content. I'll call it a victory if we can get through that. And since we haven't completed chapter 3 yet, what I'll probably do is I'll push the homework back to be due on Wednesday after the break so that you all still have something to work on before the next homework will launch. Because we can't do the next lab until we complete this chapter. We'll probably complete this chapter. We don't have class next Tuesday, right? So we'll meet 1 week from today and we'll complete chapter 3 then. And then we'll go ahead and move on to the next chapter. And we'll have the new lab too. Okay, with that said, I want to pick up where we last left off, where we were at the very tail end of control structures. Oh, that one's not working, huh? And so we left off at switch statements. Now, where in Java, switch statements seemed as just kind of a different variant of nested selection statements, if-else statements, the way that they're implemented inside of assembly is very different. So that's why we're going to regiment it, and that's why we kind of inspect it as its own thing. So here we're going to spend a little time to actually delve into or jump into jump tables. I guess that pun was unfortunately intended. Anyway, so the big thing about our switch statements is it allows for multi-branching. As we said, it compares to the nested if-else statements. And the way that they're implemented inside of assembly and inside of C, in fact, is through this concept of a jump table. So what is a jump table? It's an array where each of the entries is the address of some code segment. So recall up to this point, when we think of arrays, we think of it as a contiguous block of memory that we can hold values in. And then we can dereference those values as we need it. And then in C and assembly, we've learned that since all of our addressable memory has a numerical address, we can have a pointer, a reference that's stored, and we'd say, oh, this isn't a value in and of itself. This is the address to a space that's somewhere in memory. And so now, typically, when we think of those memory addresses, the way we've talked about those before we're introducing this concept of a switch statement is that it was data that resided inside of memory. But as we've learned, everything that's inside of our computer system is effectively data. It's stored inside of memory, including our application code itself, which means that even our blocks of code have memory addresses. So when I talk about a jump table and when I'm talking about a entry inside of this array, it's actually referencing a block of code. These labels that we've been creating are effectively aliases or identifiers to code segments in both our C. We could do this both in our C programming language and, of course, our assembly programming language. And that's every time we apply a label, that's what we're doing. We're creating an alias for that segment of code, which we've already discussed before, I believe, last lecture. And so the nice thing about a jump table is just as it's super efficient to be able to very quickly index a value out of memory, it's super efficient in being able to index a segment of code that you want to jump into. Does that make sense? Okay. So let's go back to this example here. And so I refactored the examples a little bit so to guarantee, so the book kind of changed the label somewhat. So I refactored it to be in line from the typical C code to the jump table C code to our assembly C code. So let's take and examine this a little bit in depth. First, let's make sure we understand what's happening in our traditional C code. So we're going to create our switch function here. It's going to take a long X, a long N, and it's going to take a pointer, a long pointer, a destination pointer. We're going to create a local variable, and we're going to save into that local variable the value, the parameter that's passed at X, and then we're going to switch on N, the second parameter. And so that's a long value. On the case that it's 100, we will take that value and multiply it by 13, and then we're going to break, otherwise we fall through. On the case of 102, we'll take whatever that value that was passed in, which we'll take our local variable value and we'll multiply it by 10. And now this is a fall through clause. So in the case of 102, we then fall down into 103, or on 103, we would jump to that segment of our code where we would take this local variable val and we would add to it 11, and we have a break statement. So then we would jump out of this entire switch block. Then on the case of 104 or 106, these share the same memory address effectively, same reference to this code block, which is going to be, we take our local variable val and we multiply it by itself, and then we break out. Then we actually have a default clause so that if we don't hit any of those other cases, we will just set our val to be 0. And at the very end, we'll take whatever our local variable is, and then we'll save that into that destination address. Okay, so does everyone understand this? Okay, so now the next thing is going to look a little bit unusual. We're going to do the same code, but we're going to do this exposing the jump table. So instead of using the syntax that's given to us by C, we're going to build the switch from scratch. Okay, so I'm going to define my function switch. I'm going to pass in those same parameters, X, N, and a destination pointer. I'm going to create a local variable, and I'm going to store the value of X into that local variable val. Now I'm going to create right here a jump table. And so there's a couple things you should see with this jump table. Okay, first of all, we're going to make it static. Second of all, what's the data type that's associated with this jump table? It's a void pointer, right? So again, the idea is we're not holding a data type. The data type is a void type because the thing we want to hold a reference to is a code block. Does that make sense? Okay, so we're going to hold a pointer in memory to something that's not data. So a void pointer, and then then we give the label, the identifier jump table, and then use box notation to indicate that's going to be a collection of void pointers. Then we're going to use our, we're going to create a array, a literal array, right? And inside of there, we're going to go ahead and use the double ampersand operator on each of our labels. So when we define a label, that is now an identifier, just like a variable is kind of like an identifier. We've created a marker, a space, like a bookmark somewhere inside of our code. Now, typically, when you use the single ampersand, that gives you your memory address, right? Now, the question is, when you use double ampersand, what does that mean? A double ampersand will give you the memory address of a void pointer. So it's a special operator, it's a special uni operator to be able to return the address of a label in your code. And so when we do this, since we inside of our code block have I
also searched it up, and I found that it's like a compiler extension, so it's like specific to GCC.
That's very true. It's not part of the C standard. You'll notice that actually there's some things that we'll cover inside of this textbook that's not part of the vanilla version of C that we will cover, since this is a systems class that's designed in line with using a Unix-based platform and using GCC as our compiler environment. But yes, you're right. It is a, I want to say it was introduced in what version 11 of the platform specific of GCC as a mechanism to be able to go ahead and access the memory address of your labels. Now, the other thing, since this here is an operator, this has to be the labels that we have defined inside of our code block. So we have, for instance, here, our location 100. Now, Neil, before we were using the term case, right? That was our keyword. We're going to be kind of consistent with our naming. So here, this is going to be location 100, location 102, location 103, location 104 and 106, because that was our fall through. And those would effectively be pointing to the same memory address inside of our code block, inside of where our code is. And then finally, our location default. And then the implementation after that is going to be very similar. So here we can then check on this instance that it falls outside the bounds of our case statement. So we're going to say if n is less than 100 or if n is greater than 106, then we're going to jump to that location default. Otherwise, what we're going to do is we're going to jump into the code segment that is inside this array of void pointers based off of the value that is in scope. So that means if we have, and so what we'll do is effectively we're using our numerical value as an indexer, right? So if, for instance, n is 100, 100 minus 100 would resolve to be 0, which means that we would look at index 0 in our jump table to find out what code segment we're going to point to, which would be this block right here, right? And so if it was 102, for instance, then we would go ahead and jump to this case here and whatnot. Actually, this would actually be our fall through case. So notice that at the end of each of our code segments, to ensure that we have the equivalent of a break, we have another go-to that jumps to end, where our end case is here, which is where the end of our switch would normally be. Now, if I forget to put a go-to statement at the end, clearly the not native behavior is to run each statement in sequence. So then we would just fall through to the next. So I think this kind of gives you a little bit more of an intimate idea of what's happening with switch statements and how they actually operate. And I think that's, so nothing interesting really happening with 103, nothing really interesting happening with 104. This is the default where we checked for out of bounds in the very beginning. And then finally, the very end is what we did outside of our switch block, where we took that value val and we went ahead and assigned it into that memory address at dest. Excellent. Does anyone have any questions about this? Okay, so then if I wanted to then compare that switch statement as it was in C to the way it would be actually at the assembly level, let's take a look. We will have our section block. Inside of our section block, we'll go ahead and declare our switch label for our function. Here we can see that the way that our code is defined on line 4, here we're going to move our X value into RAX because that's going to handle our computations, right? That's our accumulator register. Then what we're going to do is we're going to compute we'll take and define our index like we did before. So we're going to subtract 100 from n, so n minus 100. So the same logic on how we're effectively using the jump table as a set of indices to define our case. So we're doing that exactly the same way as before. The next thing we're going to do is we're going to compare the index to 6 to see if it's in bounds. And if it's not in bounds, then we're going to jump to default. If it's a JA is jump if above, and then the label we would jump to, which would be here, which is going to be the default behavior. Otherwise, what we're going to do is we're going to use the jump table. So here, notice we'll go ahead and we have, it's at the bottom, we have another section, and we'll talk about this in just a moment, the RO data section. RO is short for read-only data. You don't want your jump table, obviously, to be mutable. That would probably not be a good thing. And here you can see, this is where we go ahead and initialize our set of labels. So now they correspond with, they have an assignment, a void pointer memory address.
So this is this code from assembly is almost the same as the one before, the C4.
Exactly. That's the point. Trying to show you how closely we can bridge the gap between what's happening at assembly and happening with C in a way that you can take, so that it's not such a big sheer cliff, right? The idea is that assembly is a lot of text. It's a lot of instructions. It's a lot of management of your registers and having to move things around or popping things on and off of the stack. But a lot of the logic that drives it, we can emulate a little bit with more brevity inside of C. And then once we're inside C, we can then compact that more so into the set of keywords that's given to us that we're more familiar in a modern day setting. And so the beautiful thing about C is it's that like intermediary language that allows you to get very close to this level, but also be able to get very close to a very high level, right? It's a high level language that lets you get to drop down to the bottom to be very low, which is why it's commonly used in system level programming. But yeah. So the idea was by understanding what was happening before, you can see, we can step through this and you could see the logic follows exactly the same. So I guess with that said, without like beating a dead horse here, does anyone have any questions? Just looking at this, look at the comments on the right column, look at the code on the left side. I'll give everyone just a few moments, about 30 seconds, I guess, just to look at it in silence so that you can kind of follow the logic yourself. And if you have no questions, then we'll just move on.
In line 10, this I and L means I multiplier or something?
Yeah, that's right.
Okay.
Yep. And it's my goal, whenever we share any assembly code in class, to try to pair it with comments to the side to make it more readable to you, so that you can kind of look at the assembly level instructions and more clearly understand what's happening and kind of get a motivation and understanding of why it's happening.
Which dialect of assembly?
This is I want to say it's the AT&T assembly spec that the book uses, if I'm not mistaken. which inside of your assembly class, you were using the MASM 32, right? But you can see fundamentally, they're pretty similar. Okay, so we saw earlier that we create our labels, but there's also a section where we can go ahead and define our RO data, where we can actually define our jump table and what our jump table holds. And notice our jump table holds all of our labels, which are quad words, right? Because our addressable, it has to be the size of whatever the addressable space is. So we've been using quad words for that. So just as a reminder, because I think I said this on the last slide, RO data stands for read-only data because you do not want it mutable. And so this is, I think, the way that the book shows you, but I want to show you what the full code also looked like on the last slide. Okay, so some special things that we want to look through. Well, we already talked about it. The case for 102 falls through 103, and we saw how that works in both the assembly and the C. And if you know, just to highlight that in the assembly, let's find that case. You can see all the other cases, we had that jump, just like we had the go to inside of our C code. We didn't place that inside of our assembly. So just like in the C code, without the go to, without the jump, we just fall down to the next line. And then our multiple labels just map to the same code block. That should make sense kind of naively, right? Like you can have multiple variables that have reference to the same value in memory. Well, this is effectively the same thing. When we create multiple labels that don't have any instructions between them, effectively what we've done is created two different aliases to the same code block memory address. So they're just referencing to the same place. Okay, so why should we use jump tables? Well, jump tables are arrays, right? So the same reason why you might want to use an array for holding a large volume of data, it's incredibly efficient to hold a large volume of code segments, right? So it allows you to be able to potentially jump between hundreds or thousands of different code segments in a single jump table, like really rapidly, without having to do any additional jumping around inside of your code. So in terms of optimization, it's awesome. So this is the thing. In Java, you're probably told to avoid switch statements at all costs. But there's a true, real benefit in terms of its efficiency and performance and optimization, right? Because it goes all the way down towards the very kind of primitive concept of label jumping inside of the lower level languages. Now, again, the reason why you're dissuaded from that in Java is that you now exist in a high level environment, and all the optimization that you really have to be concerned about actually should happen at the compiler level. So the compiler should take and when it converts your high level code into something that's going to run as machine code, it should do all these optimization tricks for you. So you don't have to do that, and you can make your code more readable. Okay, we're done with switch statements. I'm glad that we took and put a pen into it, because I don't think we would have really done a service for that small subsection with just like 3 minutes left of last lecture. Okay, so now let's talk about procedures. Procedures are, of course, a foundation in any kind of software, including the very low level of assembly, right? We call them lots of things across different environments. So what we call at a lower level as a procedure, you might call as a method inside of a higher level language, a function in a higher level language like C, or a method in an even higher level language like C++ or in Java. You also have subroutines, which is probably what you were calling some of your code inside of assembly, Are you using procedures in assembly? Probably procedures and subroutines you're probably using in terms of linguistics. And just in terms of, just to be relatively specific, when you hear the term method, that's usually reference to something that's defined inside of a class. If it's not relegated to a class, if it exists as its own construct, then it's typically a function in a higher level language. So like you write functions in C, you write methods in Java, we write procedures in assembly. No, but it's the concept that drives procedures or methods or functions is always the same. It enhances our ability to design software because it allows us to abstract away the details of what we're working on at any time, and it allows us to effectively start declaring an interface. What is the inputs I need? What is the output I need? What can I define as my set of logic in between? And then I can piece them together like Legos. So again, all the things that drove the concepts of object-orientedness, those are the same concepts that drive procedures to begin with, right? Okay, so just to ensure everyone's on the same page, when we define procedures, what we've now effectively done is packaged a segment of our code into a small block. We've given it a label. We have the ability to send it data. It has the ability to send us back data. So let's talk about how procedures can start working with other procedures to start exchanging data and be able to offload work so that we can decompose our logic when we build an application. Is everyone familiar with the word of decomposition? Is that something that you learned in 1583? Yeah, so basic idea is that we, as computer engineers, developers, software designers, we take very complex problems and we decompose them into simpler problems, and then we create a set of interfaces between our various smaller parts so that we can assemble them together to build the complex thing from the smaller constituent pieces, right? Okay, so let's talk about how it's facilitated. Suppose we have a procedure P that's going to call a procedure Q, right? What has to happen? Well, we know that when a procedure calls another procedure, that procedure stops and it gives control to that new procedure. So our procedure P, when it requests something, says, okay, I'm going to wait for you to go ahead and do the task I just assigned. Then I'm going to pick back up once you've given me a response. So we can almost think of it as a request response model, very similar to what happens with a client and server through the internet, right? Think about how the internet works in general. If you're on your browser, you go and request a web page, and you sit and you wait until the server gets your request and then gives you a response, which is typically going to be the content that then is delivered back and then rendered inside of your browser, right? That's in a very high level way, that's how we deliver content through the internet. In a very low level way, that's how we deliver data between procedures and methods and functions and objects and everything else. Almost everything in terms of software design works on that client server model, or very many things do. Okay, so when we pass control from P to Q, we also have the ability to transfer data. So it's not just requesting an action to occur, but we can give things to Q, and then Q can give us back things. So that means we have to figure out what order do we execute our code segments in, and how do we manage the data at any given time, right? So these are the complex things that our system has to be aware of to be able to delegate when in support of procedures. Like, well, this is a complexity that now exists because procedures are a thing. Okay, so what is our control mechanism? How do we pass that control from one procedure to another? And so we use the program counter to do that, right? So you've already learned what the program counter is, probably already aware that it tracks at any given time what block of code should be executing or what line of code should be executing. We've already mentioned that it holds effectively a memory address. So we've already kind of made the intuition that all of our code blocks are memory addressable. In terms of transferring data, what mechanism do we have for that? Well, we're going to see how there are responsibilities from the calling procedure and the called procedure. And both of these have to be aware of what they have to do in order to exchange information or maintain information. So for instance, P, which is the caller, the one that's calling for Q to do something, has the ability to pass parameters to Q. And then Q has the ability to return a value to P. So how do we handle the memory for both P and Q to do that exchange, to pass input and to get data back out? Well, we're going to see how Q can allocate space for local variables. Remember, Q is the called function. So it's going to need the ability to store data to do its work. But when it's done, it should also deallocate that memory so that it does not have to be, so that's freed up for P or some other procedure to also be able to utilize it. So one last thing I should state before we actually kind of dip further into procedures is that our x86-64 architecture has a very specific implementations to handle procedures. So procedures, as you've already seen, are embedded at the assembly instruction set. Like our instruction set handles that. We've already been reading code that illustrates that, like the fact that we have labels and we're saying, oh, these registers are where our parameters go. The reason why those parameters are inside those registers is because that's part of the spec for x86. It's designed to handle procedures, right? At a very basic level. Okay, so this is our stack. This is our runtime stack. This is the data structure that we utilize to manage the control over what procedure is running at any given time, right? And again, when we say stack, we always refer to a last in, first out memory management structure. So it's going to facilitate the ability to hold our procedures. It'll give us the ability to store data at any given time for a current procedure that's running. And it'll also give us the ability to free up that data when we're done running our procedure. This is why stacks are ideal for this situation. Okay, so how does a stack function during our program execution? Well, the control and data are both added to the stack, right? You can see these segments that we have. The information is removed from the stack when we return. So each time we return, we move back, we pop the data from the stack as necessary, and we pop whatever the return address is as necessary. We grow towards lower addresses, right? So we grow downward, and the stack pointer RSP is how we track what the topmost element is. So just looking at this diagram here, I think the other slides are going to go into here. So we have our increasing addresses, right? So this will be our top of the stack. RSP tracks whatever, so whatever value is that represents our top. That's going to be the argument build area, which we're going to talk about in a moment. We can have local variables. We can have whatever saved registers we need. And then finally, we'll have a return address, because then that becomes the new, this would all get peeled off when this procedure is done. And then this will be the new memory address of the next code segment we jump to start executing. And then this would be all the data necessary for that procedure to also run. Okay, so how do we move things onto our runtime stack? Well, we have push and we have pop, and then queue is just indicative of a quad work. So that allows us to either store data or to retrieve data. And again, we can adjust the stack pointer to allocate or deallocate space. The stack frames are useful for when we want our procedures to require more than storage than our registers allow. So when we pass and we'll look at this in a little bit more, but there are instances where if you need to pass more data than you have available registers for, and this is in a future slide, but I'll just state it now, you can have up to 6 parameters that can fit. I'm sorry, you have 6 registers that are used for parameters. So the first 6 parameters, provided they're integral data, which means it's like integer data, or rather it's a memory address, then that can be saved into your register space. If it's any other type of data, or if it exceeds 6, then it gets pushed into the stack, and then you get access to those parameters from your stack frame. And the stack frame also maintains our return address so that we know where to go back home after we're done peeling off the set of instructions on the code that we're currently working on. So yeah, so stack frames can be fixed, or they can be variable size, right? We can even have some procedures that don't use a stack frame at all, which we'll call them leaf procedures. We'll take a look at them in this slide deck. Okay, so if we want to optimize our stack frame usage, if we want to try to make it as efficient as possible, then you can have procedures that only allocate the needed parts of the stack frame that you want to utilize. If you have procedures that are less than 6 arguments, then you can pass all your parameters and registers potentially. Because remember that your registers can also hold memory addresses, so references to other things in memory. And so our functions, as I stated earlier, our leaf procedures might not even use a stack frame at all. It might not require them. Okay, I already mentioned what a leaf procedure is, a function that doesn't call any other function. So if we think of a set of function calls as building out a tree, because that's effectively what we're doing. The reason why you have a main function in every application is it's the root of the tree that gets executed in your runtime stack. So it's the very first node in that executable tree that gets pushed, and then the main function should then call other functions, which then call other functions until you hit a leaf function, a leaf procedure, which doesn't call anything, so then it returns back control, and then it might branch back out. So every application should fundamentally be able to be modeled at the end of the day as a tree. So because of that, we have leaf procedures that don't push anything themselves onto the stack. And depending on what they do, they might not even need much of a stack frame in terms of reserving data onto it, just the return address to go back. You also have inline functions, which are a compiler optimization where the function code is inserted into the caller's code. And again, that just kind of reduces some of your overhead of having to create and tear down stack frames, because there is a cost to that, right? There is a cost to managing your again, more optimization techniques that can happen is trying to do as little overhead as possible so that you can just execute your code. So in the instances of leaf procedures and inline functions, they're much more efficient than non-leaf functions. But we don't care about that at high levels, right? These are just things you should be aware of at a lower level. I don't want to influence you, right, at a high level. Okay, so let's talk about some of these mechanisms. How do we transfer the control from one procedure to the next? Well, we know that the mechanism that we've used up to this point is a program counter. And so there are two functions that are utilized that allows us to update the state of our program counter, right? That's our call and our return, our ret. So for instance, the mechanics of how call and return work is call will push a return address onto our stack. And you can see when we execute what's happening right here inside the diagram with our call, where before, while executing the call and now after the call, we now have pushed a memory address onto the stack. And then when we call a pop, an address that's on the stack then gets set into our program counter. So then it gets popped off and then put back into RSP. So RSP and the stack are the things that are effectively exchanging data to manage what procedure is running at any given time. Which is why RSP is, again, the top of our stack. It's effectively the variable that, or the register that holds where we're running our code from. We already mentioned this before. I'll just highlight it again. You have direct and indirect calls. So since we're talking about calls for the stack, we can call in the same way we learned how to use calls earlier, right? So we can, a direct call means we can call to a label. A indirect call means we can dereference a register memory value and call to there. Okay, so here is an example of some disassembled code. If I wanted to read through, we can see what the exchange is between the stack and or how the stack is actually executing our instructions using those calls and returns. So for instance, on line 5 here, let's look at the call. Here you can see we're calling the mult store function, and we're pushing the return address. And in this instance, the return address is 400540 onto the stack. And then we're going to jump to that function by setting the program counter to this value. And then on line 4 here, you can see we're returning from the mult store function. And so there we're going to pop the return address from our stack and jump back to the address, resuming the execution at 400568. Okay, let's actually look at some C code and then jump into some assembly code. So we mentioned that you had leaf functions. We mentioned how there's a transfer of control. So let's look at this very basic function and then map how that transfer of control is happening. So I have leaf, it takes in a Z value, it returns Z plus 2. Here I have a function called top, it takes in an X value. The first thing it's going to do is it's going to invoke leaf, pass in the value of X minus 5. It's going to get back some value and then save that into result. Then we're going to then return that result times 2. And then our main function, because every function, every application needs a main function, we're just going to go ahead and call top, pass it the value of 100, and then go ahead and then save that into our local variable called result. And then whatever code you have after that. Okay, so here we're calling top. Top will then call leaf. Leaf will return a value. Just put that into result. Result will be mutated. Our parameter is being mutated. There's a lot of mutations happening here, right? In the parameter space, in the returning space. So let's see how all of that will then shake out. So if we go ahead and throw this through a disassembler, we can see here that we will have our load effective address, and we're going to dereference what we're taking from RDI. That's the argument that got passed in. And it's going to compute our Z plus 2 value. And then it's going to return. And then we're going to return back to top. Because remember, the very first thing we did was do main. And the first thing main did was call top. And the first thing top did was call leaf. So really, the first thing that's actually executed is leaf. Leaf is the first thing that is going to start executing our code. And then we're going to call this return. So it's going to pop that address off of the memory stack and return control back to top. And then we're going to vacate leaf. Then we're going to execute the line of instructions that's inside of our top function. And we'll do that all the way until here, where we have our return value, and then we go back to our call to our main function. So you can see you're kind of moving backwards and forwards and backwards in a way, where you see our calls and where we shed it in reverse, where we're actually executing it here. Because we're growing at the top, right? So the top is a smaller memory address. So that initial call is happening down here.
Almost like maybe an infinite address.
Exactly, yeah. Okay. Well, maybe you just make it cyclical with every possible combination of sequences. Okay, let's see here. We already talked about emphasizing the procedure. Data transfer occurs during procedure calls and returns. Yes. Okay, so the next thing that we want to talk about is going to be the data transfer. We talked about how we're able to transfer control between the various procedures using the program counter and the stack with memory addresses. So then let's very explicitly talk about how our data is transferred. So our data transfer occurs during the call and return periods when those instructions are invoked. And our x86-64 actually uses registers, as we stated, for our data transfer. So for instance, and actually let's just move down, we can actually see what registers it uses. So our arguments, when we have a set of parameters, up to the first 6 can be put into your register space. The actual registers that are destined for parameter 1 and parameter 2 and parameter 3, 4, 5, and 6 are listed here. So it's in the order of RDI, RSI, RDX, RCX, then R8 and R9. And again, you can offset those however you need. So if you don't need a 64-bit register space, you can always reference the 32-bit, the 16-bit, all the way to the 8-bit in the way that you've already learned how to do in assembly. Now, if you have more than 6 arguments, let's go back to this. And now here I'm going to highlight this inside of our stack frame. Notice we have our return address here. And then after the return address, any argument after the 6th one, so argument 7, all the way up to argument n. You can have any number of arguments, so long as you have stack addressable space for it, can then be put into your stack frame. And then that's transferred over to the called function. Okay, so let's just take an example code block of this. So suppose I have this C code proc, and it has 1, 2, 3, 4, 5, 6, 7, 8 parameters. That means 6 of these parameters can fit into our register space, but 2 of them are going to have to go into our stack. So if we actually look at the assembly level code here, we can see that our various, we can see how we're going to do our stack management to go ahead and get those additional data, those additional parameters into the stack so that it's going to be available to the called function. And so if I actually wanted to take a look at a example here, the last 2 of the parameters was A4, which is a character that's only 8 bits, right? And it was a character pointer, and character pointers are going to be much bigger than 8 bits, right? All of our pointers are the same size, quad word probably. So if we look at here, we can see, I guess in this instance, it's going to be a 6. Oh no, yeah, that's an offset. So here we can see we have our return address. And then here, you're only consuming the 8 bits. And then here, you're going to consume your entire space. Which means that all of our data has to be divisible by 8, which I think is not uncommon. Okay, let's move on. So why might we have to use the stack to push our data? Well, like we already mentioned, if you have more than 6 arguments, or maybe your data doesn't fit in a register, and if that's the case, you can always push onto the stack. Another thing you should know is any address operator, so anything with the ampersand, actually requires memory addressing. So you can't necessarily use a register itself. You can have a register that has a memory address in there, but if you actually need something to be addressable, then you might push that memory address or a reference to something onto the stack. Because the stack is addressable, right? Everything in the stack has an address. Same with arrays, right? Arrays or structures need memory-based referencing. So anything that needs memory-based addressing, you might go ahead and utilize the stack for as well. Okay, and just an example of handling the address operator. Again, if we have this code here, we have a swap add function that takes 2 pointers, dereferences those pointers and saves them in local variables, then takes the values and then swaps them with the memory, what's at the memory address, and then returns x plus y. Then what we can see here is, okay. Makes more sense when we can see the assembly side by side. So here you can see, in order to make this caller function that's going to call the swap add, we can see that we're going to allocate those 16 bytes for our stack frame here, because RSP is what effectively is the source communicator with our stack pointer. And then here, we will store our 534, so right here, into argument 1. And then we will store 1057 argument 2. So and then we can compute based off of using those address operators, right here. And again, the reason why we're loading those into the stack is because those are what I mentioned before. We're using the memory dereferencing. So you can't use your register spaces. You can't use your parameter space of registers for that. So just an example of what that was intending to say. Okay. And then we have this example here, where we can go ahead and have a call to a procedure. And very similar example as well, where we can allocate our stack frames, where we produce all of our offsets here and load data into our stack. So notice every time we want to load data into the stack, we can just use RSP because it's tracking the current memory address. And again, looking back at this procedure, you can see right here, A4 and A4. We talked about, I showed you the visualization. This is the assembly that would go ahead and do your 8-bit offset, and then your 8-bit offset, and then your full offset here. Okay, so just a couple of things you should know. Like we said, there's data from the callee and data from the caller. The caller is the one who supplies the parameters. The callee is the one who supplies the returned value. So the callee saved registers are RBX, RBP, and R12 through 15. So those have to be, if there's any data that has to be preserved and then pushed onto the stack to be brought back later, it has to. Those are the ones that it's the called procedure's responsibility, so that the callee will have access to those registers. So if you want any values there, make sure you push them onto the stack before calling a function, or you might lose them. Actually, that's always the response. Always make sure everything is pushed if it's important, or you can get it potentially overridden. Okay. And so this is just an example of an instance where there is data that we have to preserve over the course of this execution. So for instance, in this very simple function P, where we pass in an X, we pass in a Y, the first thing we're going to do is we're going to call the function Q, pass it Y, and get back a U. Then we're going to call Q again, pass it at X, and get back V. So we're going to call the same function twice. However, in between then, we're going to have to preserve data inside of P so that it can utilize its results from Q. And so we can see, if we step through the lines here, that we're going to be able to preserve that data. First, we're going to push our RBP and RBX onto the stack so we can preserve them. Then we're going to align our stack frame. Then we're going to save the value of X, because we're going to need to have access to that value of X. Then we're going to have to move Y to our first argument into RDI, because that's our parameter that's for the next function. Then we're going to call Q with that parameter. Then we're going to take what's produced, and we're going to take and move to save the result. And then we're going to move X to our first argument. So we're going to take RBP and then move that into our parameter space and then call Q again. So each time we're getting that accumulator, we need to go ahead and make sure we keep saving the results of our accumulator. And then we're finally going to deallocate that last part of our stack so we can recall and restore by popping RBX and RBP when we're done. So again, the function P is constantly pushing and pulling things off the stack while it transfers control to Q, because we know that it's going to utilize some of those registers, and we have to preserve particular data in between the calls to Q to do its work. Okay, the last thing I kind of want to talk about today for this particular subsection is going to be our recursive procedures. So we've seen how we can have one code block go ahead and transfer control to another code block and transfer data to another effectively code segment, and then how that code segment can transfer data back. It's all managed through a combination of our register spaces and our stack. So now the question is, well, how can we have a procedure that can call itself? Right, these recursive procedures. And they work pretty similar, right, to procedures that call other procedures. They still have access to the stack and register spaces. But let's take a look, for example, at this very common factorial function. So here we have rfact. It takes in a parameter. We'll create a local variable result. We'll check to see if the value that got passed in as our parameter is less than or equal to 1. If it is, we just return a 1. Otherwise, we take whatever n is and we multiply it towards another call to the same procedure name, but now we're mutating the value of n to be n minus 1. And then finally, we will return results, whether we do this if or else, right? We do some type of return. So what does this look like inside of our assembly code? We have our procedure, rfact, and actually let's take and let's pull it out some. Okay, so the first thing we're going to do is we're going to save the value of rbx. So we're going to push that onto the stack. Then we're going to store n into the callly saved register, which is rbx. So we're gonna move our parameter. So store n into the callly, so that we're moving RDI into RBX. Then we're gonna set our return value to 1. So EAX, our accumulator, will move 1 into EAX. Then we're gonna compare to see if our parameter, that's RDI, and 1 are the same. If they are less than or equal to, then we're done. So we're going to jump to L35 here, where we're going to pop RBX back out and then return control back to whatever called us. If it's not, then we're going to load the effective address of RDI, and we're going to go ahead, which is our value of n, and we're going to subtract it. And then we're going to call rfact again, and then we'll go ahead and then do our multiplication. Oops. Oh, come back. Okay. Okay, then we're going to do the multiplication of our result by n, and then move that back into our accumulator. And we'll keep doing that until we hit that break condition. Because here, we're going to call back here, and this effectively, if you look at it, when we're looking at control structures, notice recursive functions are effectively just loops, right? That have a break condition, a jump condition that allows you to break out. So when you learn that in a high level language, you could take any while loop and reframe it as a recursive function, or you could take any recursive function and reframe it as a while loop. You could see very fundamentally, they're the same thing. Okay, that gets us through procedures. I'm pretty happy with where we're at today.
So you said like that was the same as a while loop?
Let me be, I guess, a little bit more precise. The mechanism by which we can go ahead and define the control structures between recursive procedures and the way that we create our control on a while loop is very similar. Now, where they distinguish is that our while loop isn't necessarily touching RSP, it's not loading anything into the stack, right? The nuanced difference in our recursive call is that we can do all the stack management stuff that we could do with any other procedures, which kind of opens up the possibilities a little bit in the way that we can push and pull things from the stack. But the way that we're governing the control over our base case or our recursive step is very similar in the way we define our control inside of our while loops. Is that a better kind of like?
Yeah. Like a while loop, but I mean, like you have that while loop concept, but you also have the stack and store like all
Exactly.
layers.
And that's what makes recursive procedures, or these recursive definitions, so powerful. Yeah, for sure. Okay, does anyone have any questions? If not, I think this is a great breaking point. We might actually end class 8 minutes early then, which I don't think anyone will be opposed to, because I know there's been certain classes that we've gone a little over on. So I will see you all next week, next Thursday, and we will finish up the remaining part of chapter 3 next class. So I will see you all after the break. Have a good week.